In the previous video, we talked about what CS deformation is and why it is important. I'm Luisa von Almdühl, a PhD student at the Alfred Wegener Institute, and in this video I would like to explain you how we can observe CS deformation with satellites and buoys. The polar regions are inaccessible, very large and almost uninhabited. Therefore, observing them from space with satellites or with autonomous measurement systems as buoys is the only suitable approach to monitor sea ice deformation on a regular basis. Let's start with satellites. We often use SAR satellites for this purpose. Here is the example of Sentinel-1. The data has the advantage that they are available anytime, regardless of clouds or polar night, and they have a spatial resolution of 50 meters. This allows us to identify different features, like regions of pressure ridges or individual flows. On the next slide, I show you a video of such images, following the mosaic flow. Here are some daily images from Sentinel-1. Try to follow the individual flows of the ice with your eyes, while the flows are moving. This is exactly what our algorithms do to derive velocity fields. So, as I said before, we take two images and track the position of ice features or patterns on the two images. This way, we can see how much the ice has moved in between the images. Taking into account the time difference between the images, we get a velocity field. In this velocity field, here is an idealized one, there might be areas where the ice moved faster or slower. At the boundaries of those two areas, the ice is then moving apart from each other, called divergence, or it is compressed, called convergence. Mathematically, we take the spatial derivatives of the velocity field in order to obtain divergence, convergence, and shear. This, in the end, leads to deformation. An example of a deformation field is displayed here. In green, there are lines of strong deformation, while the ice without deformation is displayed in blue. We will come back to those fields. But before, let's have a quick look at the buoys. In this context, I would like to draw your attention to the booth of Daniel Watkins. He is presenting in much more detail how to derive deformation from buoys. Buoys are drifting with the ice, and they send their location often on an hourly basis. This is how we can calculate again how the velocity changes spatially by comparing different buoy velocities with each other. We construct areas of buoys by connecting them virtually by lines. The area change of those polygons is a good visual indicator of the deformation of the ice. For example, here the area of the buoys got smaller, so the ice in between them was compressed. Now we can combine and compare deformation derived from buoys and satellites. In this animation, you see the total deformation along the track of the mosaic flow for several weeks in spring. The velocity of the ice is given by the white arrows. In green, there are lines of strong deformation, while the ice without deformation is displayed in blue. The mosaic flow is in the center of the 50-kilometer circle. Looking at those really well-defined lines illustrates that deformation is often really localized in space. The changing shape of the triangle displays the deformation of one of the buoy areas. Following how the shape of the triangle changes indicates what deformation the ice within the triangle has experienced. What buoys cannot tell us is where exactly in the triangle the deformation took place. Those information are then provided by the satellite-derived deformation fields. Let's do a quick comparison as a summary. We can observe CS deformation with satellites and buoys. Satellites have the advantage that they provide a high spatial resolution of the deformation, and this even over large spatial areas. The buoys, however, have a higher temporal resolution, and their spatial uncertainty is often lower. If you want to learn more about the mosaic time series, have a look at the next video.